Okay, hello. I might be absent tomorrow, Tuesday, or tomorrow's Tuesday, yeah, because my daughter's ill. So if I am, all the answers should be posted online, so it should be pretty self-explanatory. One thing I do want to mention, when we draw the field lines for permanent magnet, the fields kind of come out of we define it as the fields coming out of the come out of the north side of the magnet and enter the south side of the magnet, the permanent magnet. You should probably, though, also maybe include these dotted lines. Now for magnetic field lines, the one thing that's incredibly important, and I mean incredibly important, is that the magnetic field lines don't start or end in a single location. It's a continuous loop of field lines. It's kind of continuous. And notice the magnetic field lines of this bar magnet are essentially identical to the magnetic field lines of a solenoid, which I forgot to put on here, fiddlesticks, of a solenoid. I guess this is a solenoid. The magnetic field lines of a solenoid. So here's a solenoid. And so the magnetic field is going to go outwards. It's going to go up and around, and it'll look identical to that. It'll look identical to that of a permanent magnet, which is kind of cool. Okay. Now, one thing we're going to do a little bit of review on, I should probably have done it like this. I regret my decisions. So magnetic field lines never cross each other. And for magnetic field lines, they're always this way. And they're always like a continuous loop. It never stops and starts. And that's different than what we saw with electric field lines. So I don't know if you remember electric fields, but for electric field lines, if I have a point charge, the magnetic field lines start at the point charge and they end out either towards infinity, or if there's a negative charge, they would actually terminate at that negative charge. But for magnetic field lines, it's always a loop. It's always a loop. Because we have never ever discovered a single north pole. We call it a monopole. It's never been discovered in nature. North poles always come associated with the south pole. So they always terminate at that south pole. Now they might have to travel a long distance to come back and terminate, but they always kind of or to come back to that south pole. And again, they never really terminate because we imagine that the magnetic field lines continue through the bar magnet. A little bit of review. Remember Gauss's law? The surface integral of E dot dA is equal to Q enclosed over epsilon naught. So for example, here's a charge. If I want to find the electric field here, it's pretty easy to do. All I have to know is the Q enclosed. If this is Q, that just becomes Q. And the area of my Gaussian surface. And that's really all I need to know to find the electric field. Now we can do the same thing with magnetic fields. You don't need to write this down, but just keep this in mind. So here's the Gauss's law for electric fields. Gauss's law for magnetic fields will look the same, except we replace the electric field with the magnetic field. And I'm just going to stop there, equals something. And we call this magnetic flux. Magnetic flux, not electric flux, magnetic flux. Something to keep in mind is that, let's just draw some sort of Gaussian surface. And imagine this is a 3D surface. I know this is only two-dimensional, but imagine it is three-dimensional. And what do you notice about this flux? The magnetic field lines entering the Gaussian surface and the magnetic field lines leaving it. I notice that the same number of lines enter and leave it. It's the same. Which means that this flux is always equal to 0. And I could draw this really anywhere. I can draw any shape. I can draw some really weird shapes or something like that. And no matter how I draw it, the same number of lines exiting and entering, this dot product will always equal 0. So this is Gauss's law for magnets, for magnetism, that this surface integral B dot dA is always equal to 0. And this law, Gauss's law for electric fields, and this law, Gauss's law for magnetic fields, are incredibly important when we start talking about light. They're known as Maxwell's equations. You might have read these in the book somewhere or saw in some video. These are the 2 of the 4 Maxwell equations, and they are true always, always. If we were to find a magnetic monopole, this would not be true, but this it would be equal to something else. But these are true always, regardless of how fast you're moving. They're some of the most basic laws of nature that are kind of always true. And in physics, we make a lot of approximations. For example, F equals ma is true, assuming you aren't traveling close to the speed of light. These two are true even if you're traveling close to the speed of light. It's pretty cool. But that's the homework. Now let's move onwards to the next thing. So on your document, so you should be on the experiment current carrying wire, and we're going to jump to this really frightening thing called the Biot-Savart law. And I'm probably mispronouncing it because I'm not French, but you can look up how to pronounce it properly. But the Biot-Savart law is very similar to Coulomb's law. So you remember Coulomb's law, or at least the electric field of a point charge is equal to kq over r squared? Biot-Savart law is the magnetic field for a very short segment of current carrying wire. Very similar. It's equal to some constant, mu naught over 4 pi. Here we have a constant. This is 1 over 4 pi epsilon naught, if you remember correctly. Divided by r squared, times I times q, and then we have this really weird dl cross r. What the heck does that mean? This is a cross product. You probably haven't learned about these yet. If you have, great. If you haven't, here's kind of a quick summary. So A cross B is kind of defined as AB sine of theta, the angle between these two vectors. So for example, if I have vector A here, and if I have vector B here, and if I want to know the cross products, I need to take the sine of this angle between them, the theta. Okay. Now, what direction would this vector be when you take the cross product? It's actually perpendicular to both vectors. And you can find it with a right-hand rule, another right-hand rule, which we'll get into later. But essentially, A would be your forefinger, B would be your thumb finger, if you make this like cool like thing with my finger. And then the cross product would be your thumb. So A, B, and so the C would be into the page with my little drawing here. Now this essentially says the cross product of between the length, a tiny segment of this current carrying wire, it's called DL, a tiny segment, tiny length of it, crossed with R. R being like how far, where do you want to find the magnetic field? This is R. But it's not R, it's actually R hat, which means in this direction. It just tells you a direction. R hat is defined as, it's a unitless, that's not true. It's a unit vector, that's the term, unit vector. So it's always equal to 1, so that's where the 1 comes from. It just tells you the direction. So it tells you the direction. So this is an R, this should be R. And then R hat would just be like this tiny little vector with a value of 1 in this direction. This is R hat. And then sine of theta. So Biot-Savart law, look how nasty this looks. Like this looks nasty. And it's going to get nastier. So we're going to try to find the magnetic field. Let's imagine I have a line charge, current on a wire. I want to find the magnetic field here at point P. And to do this, we are going to integrate, very similar to how we integrated for this problem. We have a charged rod, and I want to find the electric field here. And we integrated all the tiny DEs, we plugged in Coulomb's law, then we integrated and you found an answer. I will do one for you. Actually, no, I'm not. I'm not going to do one for you. What I would like you to do is to do part 2. I think this is probably the easiest to understand. You're going to go to this video. That's a 0. You're going to go to this video, and I would like you to explain each step of this process. Each step of this process. Each step of this process. To find the magnetic field here, if I have a loop of current. Find the magnetic field right here at the center of the loop. So please do that. Try to understand each step. This answer, what you're trying to get to, you'll probably have to memorize this. You should probably memorize this value. And after you do this, you can flip to part 1. Part 1 is a little harder. So this is a current carrying wire, but it's straight, and you want to find the magnetic field here. And you can just look, you don't have to go to the video. You don't have to go to the video unless you really want to, but just appreciate how disgusting this looks. Absolutely disgusting this looks. And no, there's a simpler way to do it. There's a much simpler way to do it. In fact, you probably won't be asked to ever actually use the Biot-Savart law. You probably won't actually be asked to use the Biot-Savart law on the test, I think. But it's important to know where it came from, and we definitely need to know the results. But to find the magnetic field of a long straight wire, which we actually know the magnetic field of a long straight wire, it's mu naught I over 2 pi r. We found this experimentally. But to find it theoretically, we could use Biot-Savart law, or we can do something a lot easier. It's called Ampere's law, which I didn't print out. I forgot to print out. Pause the video. Okay, I'm back. This should have been handed out to you. So this is a much easier way to find magnetic fields outside of surfaces, but it only works for a few geometries. It's called Ampere's law. Again, it's not pronounced Ampere, but again, I'm not French, so my apologies for mispronouncing things. But it's very akin to Gauss's law, except it's actually even easier to use. So Gauss's law, again, the only thing that affected the electric field was the charge enclosed, similar to Ampere's law. The only thing that affects the magnetic field is the current enclosed of a loop. Now for Gauss's law, you're drawing three-dimensional surface, like a Gaussian pillbox, like a three-dimensional cylinder or something like that. For Ampere's law, it's not three-dimensional, it's two-dimensional. So you draw a loop. For example, this is called a Amperian loop, I think is what the term is. So imagine we have a current-carrying wire. The current is going in out of the page towards you. And to find the magnetic field outside of the loop, we can draw an Amperian loop outside of the loop, a distance r away from the center, little r away from the center. The current enclosed in this case is just I. It's pretty easy. It gets a little harder when you go inside of the wire, but outside it's just I. And the dl, assuming that the magnetic field and the length are in the same direction, because you know the magnetic field actually goes this way. So by my right-hand rule, the magnetic field is going counterclockwise around this wire. And so if my loop and the magnetic field are in the same direction, this dot product just becomes b times the length of your loop. And the length of my loop is just 2 pi little r. But anyway, and you can use this to find Ampere's law. The only other things that you need to know is something called current density, J, which is current divided by area, and something called a solenoid turn density, little n, which is the number of turns divided by length, but you'll get to that later. But essentially, I'd like you to watch some videos and try to explain the math. Watch some videos, try to explain the math. Again, there's only like 3 or 4 geometries you'll be in charge of. One is a straight long wire. Another is a solenoid. And a single loop and a solenoid. I kind of skipped the single loop one. And for your homework, the third one will be the torus. So later you're going to have homework, and a torus will be a third loop, which is just like a solenoid wrapped into another loop. These are super important, actually. But yeah, so that's it. So I'd like you to watch those videos, try to explain why in terms of the math. And so the videos are listed here, the videos are listed there, and then just follow all the instructions on Canvas. Okay, that was a long video, way longer than I thought. Sorry, bye, okay. Hopefully I'm here tomorrow.